Boom. And I spared that off of the recording. So how what about you and you and you? How much are you two? How much have y'all studied RC circuits? LRC circuits? AC? Did y'all do phasers? I mean, did y'all do resonance? Did you look at resonance? How that works?
Yeah. Now that I'm looking at it, I think we talked about it, but like we didn't delve into it.
Okay, well, I'm sorry, but as far as I'm concerned, that's like taking you to the pizza shop and saying, okay, this is how you make the dough, this is how you make the sauce, and then we're even going to look at this is how you make the pepperoni and the sausages, and here's how you make the cheese. All right, now, you got all that? Good. Throw it all together and bake it. And then leaving without ever getting to bake a pizza or have one. You know, well, the fact is that the book stops way short of where it should as far as resonance is concerned. So I want to try and cover what the chapter covers, but then I've got some more that I want to add to it after that. Let's go ahead and see what we can get accomplished. Last time we were talking, we looked at the stored energy in a magnetic field. Okay, so you've got an inductor. You apply a voltage to it. The current starts to build up until it reaches a steady state, and then it stays there. Well, once it's a steady state, as long as the current's not changing, the inductance is it just stays at a steady state. The magnetic field is no longer changing, and when the magnetic field is not changing, it's not inducing any countercurrents in the inductor coil. It's just there. But there is energy stored in that magnetic field, and that's how much energy is there. Pointed out how this looks very suspiciously like kinetic energy for translational motion or rotational motion. The point is, when you turn off the voltage to that inductor, that current starts to dissipate, starts to drop. This stored energy in that magnetic field is going to continue to induce current in that coil while it collapses. So we looked at the equation for how the current changes in an inductor. You first turn on the voltage. It increases according to this exponential rate, where tau is the time constant, is equal to L over R. And the current will start, initially is going to still be zero, and it's going to start to increase exponentially till it reaches its maximum current, whatever maximum current there is. Then, when you turn it off, you've still got this stored energy stored in the magnetic field. As that magnetic field is collapsing, it's continuing to push current. So the current doesn't just shut off instantly as soon as you turn off the voltage. The current dissipates. It drops exponentially according to this equation. Everybody make note of these two forms. Okay? It's not hard to, you don't have, even if you can't remember which one does what, all you have to do is think about it. When t is 0, this is e to the 0, e to the minus 0, it's still 1. 1 minus 1 is 0. So at t0, this is still 0. Here, at t0, e to the minus 0 is 1. So your current starts off at t0 at its maximum value. Okay? That's how you can sort through in a crunch when you're trying to take an exam and remember which equation does what. That's how you can look at it very quickly and remember which one does what. Okay? Now, let's talk about how current changes when it's constantly changing. This is what happens when you put an inductor in a DC circuit, okay? Which is like, that's like putting a bicycle in your aquarium. It might look good, but the fish aren't going to do anything. The fish is never going to ride a bicycle, okay? You're not an inductor in a DC circuit, then I'm not going to say they're never useful. There are times when they're helpful. They call them chokes, I think, so that if you've got like a sudden surge in current, they'll kind of help protect against current surges, keep from frying whatever you've got them powered into. But in terms of making them actually useful, you need an AC signal. You need a constantly changing current. So if the current is changing, with time, then that inductor is going to be constantly at some inductance, some value of inductance. It's always going to be opposing the change in current. That's I as a function of t. Does everyone understand what this equation means? Your current source, your voltage source, is an AC signal. Then it's putting out some V naught or V peak at some frequency. Okay? Well, 2 pi times that frequency is the time it takes, is the number of cycles per second in hertz, okay? So, if this is cycles per second, and then you multiply it by seconds, it leaves you with some number of cycles, or some number of degrees, or some portion of a circle. And at 0 degrees, cosine is 1. At 90 degrees, cosine is 0. At 180 degrees, cosine is -1. And at 270 degrees, it's back to 0 until it comes around to 360 degrees when it's back to 1 again. So, when you apply this to a resistor, the current through the resistor, it's not, now, I'm going to point something out to you here, just for my own sake. You really need to understand that there is no such thing as a pure component. Whether you're talking about a resistor, or an inductor, or a capacitor, or even just a piece of wire. There is no component of any circuit that is purely one or the other. Everything is some combination of all of them. Even a piece of wire. It has resistance. Very tiny resistance, but it has some resistance. It also has some inductance. And it has some capacitance. You may remember when we studied capacitance, we did the lab. When we looked at the capacitance of the Van de Graaff generator. Okay? There's no second plate there, but you could still build up a charge. It had capacitance. A wire has capacitance. A wire has inductance. A resistor, you put a resistor in a circuit. It is mostly resistance. But it has some inductance. It's a very small amount of inductance. It has some capacitance, a very small amount of capacitance, but there is some there. Same with capacitors and inductors. And there's no such thing as a purely inductive inductor. It's going to have some capacitance. It's also going to have some resistance. So, as you get into your careers, you're going to discover that when you start analyzing some circuits, you're going to have to take these sort of things into account. especially when you start getting up to very high frequencies. What happens at very high frequencies? Even a little bitty tiny inductance can become a fairly significant reactance. At a very high frequency, what happens to a very small capacitance? Very high frequencies, it becomes kind of like a short. Okay. Point is, I just wanted to point that out to you before we go on, because we come back, we're going on into optics, and this part of the course seems to be the more germane to your chosen field of study. So if I'm trying to add a little bit extra than the book, then you understand why. Okay, well, we're still going to pretend like these different components are purely whatever they are with no stray anything else. So when we apply this voltage to a resistor, we get I naught. I know the book calls it P, I naught. I'm going to call it P, because y'all know what a peak voltage or a peak current is, right? Okay. And there is no phase shifting. As soon as the voltage is applied to the resistor, that's the current that flows. So and I'm going to try and do these in color. So you have this voltage applied to the resistor. It's going to give you some current that changes just like this. The current is going to react instantly with the voltage. They're going to be in phase. The phase shift between the voltage and the current is going to be zero. But when you plug in an inductor, the reactance is now going to be 90 degrees out of phase. This is what that looks like. The current in that inductor is going to be at its maximum when the voltage is changing been a lot of years since I've had to work through this. Yep. I'm drawing. Keep tracing the wrong lines. There. Let me, this Look back at equation 21.9 under self-inductance. And we're going to see that the voltage induced by an inductor is equal to minus L change in current divided by change in time, right? Now, that means when you put an inductor here, the voltage drop around this circuit by Kirchhoff's voltage law has to be 0. That means voltage plus the induced voltage is equal to 0, or voltage minus L delta I over delta T equals 0, which means the voltage is equal to L times change in current times change in time, or voltage divided by L equals change in current by change in time. Point is, the voltage, the current here, is going to be changing the least. The current is changing the least. Its slope is 0 when the voltage is 0. Is changing the most. When the voltage is changing the most, the current is changing the least. When the voltage is changing the least, the current is changing the most. Okay? The net result is that it's out of phase by 90 degrees. And of course, if we were looking at a capacitor, and I want to make sure I don't draw it backwards again. Current in the capacitor is going to be 90 degrees out of phase the other way. Now that means that the current in the inductor and the current in the capacitor are how far out of phase? They're a full 180 degrees out of phase. All right. Now here's where I'm going to start diverging from the book. We talked about reactance last time. The inductive reactance is 2 pi FL. Capacitive reactance is 1 over 2 pi FC. Right? So that gives you not resistance, but impedance. Was everybody even here last time? Y'all remember us talking about that? Okay, well, total impedance, Z, is equal to the real component. Am I missing something?
No.
Oh, okay. Is the real component, which is your resistance, plus the imaginary component, which is your reactance, X sub L or X sub C. Now the book, they don't use the imaginary number, the I here, to put it in rectangular coordinates, which is probably why they stop at just adding the three in series together. Okay, but I don't want to just show you how to add them together in series. I want to show you how to put them together in parallel. How much did y'all study resonance? And filters and things? Okay. Did you? Okay, well. All right, so we put in 3 components in this circuit. We've got VP at some frequency F. There's our resistor. There's our inductor. There's our capacitor. Now, X, the reactance, like resistance, is measured in units of ohms. Kind of just the same way work and energy are both measured in joules. Okay. The way you would write this is the total impedance of this circuit is, well, R plus I times X sub L minus X sub C. Because the signs of the reactance components determine whether they're capacitive or inductive. The inductive reactance is positive. The capacitive reactance is negative. If there was no inductor here, then the Z would just be R minus I X sub C. Okay? Depending on the value of the capacitor and the value of the inductor, the total, the net reactance might be positive, in which case it's an inductive circuit, net inductive circuit. If the capacitor is larger, then, or if the capacitive reactance is larger, then which would actually mean the capacitor is smaller, but point is, if the capacitive reactance is the larger component, then this would be a negative number and it would be a net capacitive circuit. Now, we worked an example, I think. So I'm just going to pick some numbers here. Let's say this is 100 ohms. This is 200 millihenries, and this is 10 microfarads. I don't know. And the frequency is 1 kilohertz. All right, well, our resistance is simply 100. So our Z is equal to 100. That's the real component, or the resistive component of our total impedance. But it's now going to be equal to X sub L, which is 2 pi F times 200 times 10 to the minus 3, 200 millihenries, minus 1 over 2 pi F times 10 to the minus 6, or 10 times 10 to the minus 6 farads. Now, with frequency at 1,000 hertz, that becomes 1,256.6 ohms minus 10 microfarads. And over 15.92 ohms. So we obviously have a net inductive circuit. Of 1240.68. There should be a little ohm sign there. That is the total impedance in rectangular coordinates. But what is the net phase shift? Because you're going to have one current flowing. And you want to know what is the phase shift of that current relative to that voltage. So we need to convert Z into our polar coordinates. So its magnitude of Z is equal to 100 squared plus 1240.68 squared square root. So we got 100 squared plus 1240.68 squared equals, take the square root, 1244.7. That's our net impedance. So if our peak voltage is, 20 volts, and that's our net impedance, is going to be 20 divided by 1244.7, which will equal 16 milliamps. That's our total peak current. And the current, of course, is still going to be sinusoidal. The question now is, how much is it phase shifted from the voltage? Well, what is the angle of our net impedance? It's going to be the inverse tangent of the imaginary, the real, which is 1240.68, divided by the real, 100, or the y over x. And that gives us an angle of 85.4 degrees. That means the current is not going to be a full 90 degrees out of phase. It's only going to be 85.4 degrees out of phase. Now, how do we get this? We've already looked at how to add these rectangular, we put it in rectangular coordinates, and you add the real to the real, the imaginary to the imaginary, and that's your sum, whether you're adding or subtracting. In order to find the current, we have to divide. So we define the voltage as 0 degrees out of phase, and divide that by our impedance at plus 85.4 degrees. out of phase. Our voltage is what, 20? And our impedance is 1240. And our angle is 0 minus 85.4 degrees. So, our current then becomes 16 milliamps at an angle of minus 85.4 degrees. That's how much it shifted. When you're multiplying you're multiplying two vectors, or in this case, two phasors, you multiply the magnitudes and you add the angles. When you're dividing, you divide the magnitude and subtract the angles. Okay? Is any of this familiar? Is this what y'all have already studied and how y'all went through and worked all this? Okay. Now, last thing they talk about in the book is resonance. Well, what happens if X sub L and X sub C, and I did this wrong because this should not be X sub L, this should be just L, and that should be just C. But what if X sub L and X sub C were exactly the same? What if X sub L was 250 ohms and X sub C was also 250 ohms? It would be the resistance only. That would be your total Z. That would give you the minimum amount of impedance, total impedance. But that inductor doesn't go away, and that capacitor doesn't go away. Their effects go away. At resonance, you're going to find, what you're going to discover is something called a Q rise in voltage. Okay? And you're going to find out that even though you only apply 20 volts to this circuit, you can end up with a very large voltage across this inductor, much larger than the 20 volts applied. And at the same time, the opposite voltage across here. Because at any point in time, Kirchhoff's law is going to have to apply. When they're equal, the voltage dropped across here is going to be positive, while this one is negative. And so even though they're very large, they cancel out. They still sum to zero. Kirchhoff's is not violated. Let's look at this just right now. We're talking about a 16 milliamp current going through a 200 millihenry inductor. What's the voltage across that inductor? How would you calculate the voltage dropped across any resistor? Current times the resistor equals the voltage. Well, we've got 16 milliamps flowing through 1256 ohms. What's that voltage? .1 volts. How did we get more voltage across that inductor than we applied to the circuit. What's the voltage across this 10 microfarad capacitor? 16 milliamps times minus 15.92. What is the voltage we're dropping across that? $255 millivolts. We've got 255 millivolts here, or a quarter of a volt here, and 20.1 volts here. But at any one point in time, and if you went through as an exercise and you plotted out the voltage and the current across every component here, across every component as a function of time, you would see that at any one point in time, Kirchhoff's law would still be applied. At whatever moment in time, this voltage plus this voltage plus this voltage will equal that voltage. But it can become quite pronounced. Let's, if you, and I don't have time to go through a whole example of this because I also want to show you what happens when you put two reactive components in parallel. What do you think happens to them when you hit resonance? This one, when they're both equal, but at resonance, and they're in parallel, you have the product divided by the sum. Okay. Point is, you go through and do the exercise, you'll find out that they become a much, much higher impedance. Their impedances add together, and they become a stronger impedance. Let's see if we can work through the example. Of course, to do the example, we need values that are at resonance. So let's use these values, 200 millihenries and 10 microfarads. At what frequency will they be the same reactance? 2 pi f times L is equal to 1 over 2 pi fc. When those two are equal, that's resonance. So we multiply both sides by 2 pi fc, we end up with 4 pi squared f squared is equal to 1 over L times C, or F is equal to 1 over 4 pi squared LC to the square root, or 1 over 2 pi times the square root of LC. So, let's find out at what frequency 10 microfarads and 200 millihenries are at resonance. Looks like 112.54 hertz. Okay, well, let's see. At 112.54 hertz, the 200 millihenries gives us 141.4 ohms. 10 microfarads would give us 141.4 ohms. Okay. What's the net impedance now of the circuit? Just 100 ohms. This is 0. What's the current now? (20 volts divided by 100 ohms, and the phase shift is 0, so just 20 by 100 is what? 50, 0.2. 200 milliamps. Okay. What is the voltage across the inductor? The inductor is 141.4 ohms at plus 90 degrees. What's the voltage? What's the voltage across it? 200 milliamps times 141.4. How much? 28.3 volts. Same thing with the capacitor, except it's at minus 90 degrees. So they're 180 degrees out of phase. They're always going to add to 0. But you're getting 28 volts, 28.3 volts across both of them when you're only putting 20 volts on the circuit. That is called a Q rise in voltage. The Q is the impedance divided by the resistance. Okay? Well, what if instead of 100 ohms, what if the only resistance in this circuit was just the trace resistance of the inductor? Say instead of 100 ohms, it's 0.1 ohms. Now, what's the voltage across the inductor? What's the current through the circuit? The current is now 20 volts divided by 0.1 ohms. Or 200 amps. What is 200 amps times 141.4 ohms? Now you got 28,000 volts across that inductor. You've also got an opposite 28,000 volts across the capacitor. And yes, you can build resonant circuits that produce those kinds of voltages, even from little bitty tiny batteries. Okay? Now, they ain't going to have a lot of power, so if you load them even a little bit, it goes away quick. But you touch it and it will knock you in the dirt. Yeah. Now, one last thing I want to look at. Y'all probably don't work with transistors anymore, do you? Okay. Ever do a Class C amplifier? Okay. Oh, I wish I hadn't erased all of that. What was the 200 milliohms? 200 millihenries, 10 microfarads. Resonant frequency was 141.4 hertz. Oh, okay. What happens now when we put these in parallel? Does anyone remember what the reactances were at resonance? Yeah, I can recalculate them pretty quick. No, okay, well, let's see. We got 200 millihenries times 10 microfarads, square root times 2 times pi, and no, the resonant frequency was 112.4, something like that. Yeah, 112.54. And that put the reactance at 141.4 ohms. Okay. Now, back where I wanted to be. What are these now that they're in parallel? How do you add them? You've got x sub L, and here's x sub C. Now, you can do the 1 over the reciprocal of the sum of the reciprocals. Okay? So that still works, but we don't have but a few minutes left, so we're going to take the shortcut. We're going to do x sub L times x sub C over x sub L plus x sub C. Say again? No, not quite. X sub L times x sub C is 141.4 at 90 degrees times 141.4 at minus 90 degrees is equal to 141.4 squared at 0 degrees, which is 19,993.96. ohms at 0 degrees. What's the sum? Well, to add them, we have to put them in rectangular coordinates. So x sub L is 0 plus 141.4 ohms, and the x sub C is 0 minus 141.4 ohms. What's the sum? The sum is 0 plus 141.4 minus 121.4 is plus I0, which means the magnitude is the square root of 0 plus 0 squared plus 0 squared is 0 at an angle of, what's the angle of tangent of 0? 0 divided by 0 is undefined. Okay. But point is, it goes to 0. If you had a circuit that was literally 0 resistance, remember I told you that that never happens. Even an inductor has some trace amount of resistance. The point is, this is going to go to almost 0. That means this is going to go to this. This right here is going to shoot to the moon. It's going to approach infinite resistance as you approach 0 resistance. Okay? Let's say, just to keep things simple, that the resistance is pretty big. It's all the way up to 1 ohm. Well, then that means your parallel configuration is 20,000 ohms. If you get that resistance down to 0.1 ohms, it becomes 200,000 ohms. Now, you fall away from that, and it goes away quickly. But what if you're building that Class C amplifier? If you remember your regular amplifiers, right? You could bypass this with a capacitor, so it made that go away to get the gain up, and the gain becomes this. The gain of this amplifier is proportional to R sub C. You want more gain, you increase R sub C, you lower R sub E. So you put the capacitor on R sub E and it acts like a short. It goes away, it goes towards 0, and the gain goes up. Now what happens if you replace R sub C with a tank circuit at frequencies above resonant frequency? This capacitor starts acting like a short. So the total reactance of the tank, this is called a tank circuit, by the way, and because of the way it works, you get these enormous currents oscillating back and forth, storing up potential in the capacitor and in the voltage across the capacitor and in the magnetic field around the inductor, and then those discharging back into each other, and you end up with some really enormous currents flowing back and forth in that tank circuit. But that's when you're driving it at resonance. When you're above that resonant frequency, this acts like a short. It goes to 0, and the gain of the amplifier heads towards 0. If you go below the resonant frequency, then the inductor starts acting like a short. And the impedance of the tank circuit heads to 0, and the gain falls off to 0. But if you drive this amplifier at the resonant frequency, you get this huge spike in gain. And it only amplifies at or near that frequency. Okay. You start working on filters, you can use these tank circuits and RC circuits to design filters that allow certain frequencies to pass and other frequencies get blocked or just dissipated to ground. And depending on how many stages of filter you build, you can, right here I show this pretty abruptly. If you looked at it in reality, if this is frequency and this is resonant frequency, what you would see is something that builds up to some maximum gain plotting gain as a function of frequency, you'd build up to this maximum gain right here. Okay? And it doesn't fall off immediately as soon as you get off of that. It takes a little while for it to go. But you can add stages and you can increase this to make it very sharp like that. You can do the same thing with just passive filters, where you can, you have the frequency response of a circuit rolls off at a gradual slope, or you add enough stages and you can drop it off abruptly. But in order to do this kind of stuff, you need to know how to calculate RLC circuits and not just add them, but to actually put them in parallel and in series and do complicated circuits. And if you get through it, you get into it, and you start analyzing the currents and the voltages that are developed, you're going to find yourself shocked and surprised. I told you I used this kind of a setup. What I actually used was a multiplier circuit, which is just RC. There was no inductance involved. But I still managed to build up 25,000 volts just from with like, I think, eight little capacitors, like 8 stages, and diodes. And it was like from a couple of little AA batteries, and I was cranking out 25,000 volts. Not very much current. Same thing applies as with the transformer. You're only going to get your power you're never going to make free power, but you will shock yourselves literally if you're not careful. But you will surprise yourselves at just how much current and voltage you can apply in these things. And yes, the currents in a tank circuit can become big enough that you will find yourself melting traces on a circuit board and have no idea why, until you realize that you've set up a tank circuit somewhere, maybe not even intending to do so. So, I know I covered more than in the book. Forgive me. Anyone have any homework you want to turn in?